Next, we have Robert Mills presenting surviving and thriving for 5 to 10 years. So,
Turn on my. Thank you. I'm going to start out and just say 2 things before I start into the slides. And the 2 things are, one, figuring out this problem is fundamental to living on Mars, or for that matter, anywhere else for any length of time. It's unreasonable to expect you can send people there for a year or 2. And if they go for a 2-year mission and they miss their window, it's 4 years. Taking the amount of supplies needed is nearly impossible. Even with Starship, the amount of supplies you need to support people for extended periods of time is pretty enormous. So the second thing is, I don't know the solution to this. What I'm going to present is what we know now, what we have yet to develop, and a reference model, which is more science fiction than reality, but to help inspire you that we can solve this problem. So from that point, I will start. We all have a shared vision that we have to leave the Earth. To do that, though, we have to find a way to use a nearly closed loop system. The resources are going to, especially in the early days, when you're talking about small habitats and small groups of people, the resources are going to be very scarce. We're going to have to rely on closing the loop on as many things as possible. We also, and especially in the early days when we haven't really looked for life well enough, and we have to protect the Martian environment as well. And so using as much closed loop as we can helps not pull in the outside resources as broadly. So that's where we start. I'm going to talk about what you actually need to survive and thrive. What do humans need? What technology and biological systems will they need? How can it work for years without an unreasonable use of resources brought in? How do you do that? And for my assumptions, I'm assuming it's a small habitat, a 4 to 8 per people habitat. That redundancy and fault tolerance is extremely necessary. You cannot just solve this problem. People's lives depend on this, and it has to go on for long periods of time. So this whole process needs to have a high level of redundancy and fault tolerance. You have to accept there's always some losses. There's no such thing as a true closed loop system, especially in early days. You're going to have, every time you open a door to go out in a spacesuit, the airlock is going to lose some atmosphere. Every time you process water, there's always some losses. So you have to accept that. And especially in early days, there's going to be some things that have to be imported. You aren't going to be able to make microchips. You aren't going to be able to have a lot of the supplements for food, such as vitamins and minerals. Some of those things aren't going to be reasonable to produce on the level you need, and so you're going to have some imports. Now, you can either talk about those as incoming imports, or you can talk about, I just brought a large stock of them at the very beginning and froze them until we need them. But either way, those are assumptions we have to make. The vision is starting with the need for clean water, breathable air, food, building materials, that you use only waste, dirty water, Martian air, food scraps, recycled supplies, electric power, local ice, and a source of nitrogen, and you're able to remake that into usable materials, and back into the air, food, building materials, and water that you need. To do that, you have to talk about atmospheric management, you have to talk about wastewater management and water management, and you also have to talk about how you're going to produce the food and materials. And as again, I'm going to say, this is only a concept to fire your imagination. I don't believe that the things I'm proposing are going to be accurately right. In fact, probably what's needed next, and I'd really like to be involved with somebody who is doing this, university perhaps, we need a good computer simulation trade study to look at all the different technologies that are possible and try and swap them in and out and optimize what is the best way to attack this problem. I know that the ISS and NASA have done a lot of pieces of this. They're very good work, but they've not done anything that talks about a 5 or 10 year process. They're talking about things where like the ISS is a good example, where you're restocking things every few months. So imagine, if you would, a 50 cubic meter box, like a shipping container, that contains all the hardware that you need to do this kind of a process. In addition to that, you would probably have plants and other things that are in a habitat, but a box that you could park next to a habitat or build into the habitat, but that would have all the equipment that's needed. Assumptions, there are many assumptions. One assumption I'm making is based on papers I've read and experiments with things like the biosphere. It seems unlikely that you can do this with an entirely biological system. So I'm talking about a hybrid with both mechanical solutions and biological solutions tied together and managed by a very high-end AI computer type process to balance it all. I'm not assuming that these things will stay stable on their own. And especially in the case of something failing or needing repair, you're going to need the ability to rebalance things in different ways fairly dynamically. A system, you have to assume that people are part of the process. They're going to have to clean filters. They're going to have to replant plants. They're going to have to do all the things that are necessary. It has to be designed with a minimum of parts and complexity and fault tolerance and redundancy. So after you figure out what you're going to do, you're going to build a laboratory model of this concept. And then that laboratory model has to go through the Elon Musk process of stripping out everything that's not necessary, reusing single pumps for multiple purposes, and simplifying it down to a practical solution. And that requires a lot of work that has never been done. Once operational, though, and once you have one that actually works, then it can go to a manufacturing process, and you can duplicate this for many habitats, for use on the moon, use in many situations. I'm assuming the food needs to meet a requirement for being palatable, but it doesn't need to be recognizable. And what I mean by that, it has to taste good, it has to be something people can eat for years, but it's likely to be things like ground mealworms and protein powders made, but run through 3D printers and things. And I'll talk about this some more, but it has to end up in something that people could actually live with for an extended period. There was a guy in 1960, and I just threw this in, who planted a little garden inside of a bottle. And that crazy garden is still alive today. And it's been a sealed bottle ever since, except for he opened it once and put some water in. That kind of shows you that a closed loop system can work if you get everything balanced correctly. This is an interesting chart. This is what does it take to keep people alive. This gets more into the details of things. You have to have a process for oxygen, carbon dioxide, nitrogen, humidity management, and a purification of the atmosphere. It can't be stinky and miserable, and it can't continue to build up contaminants. So you have to have really excellent filtration processes, and you have to have emergency reserves. You have to assume things are going to fail. You have to assume there might be a leak in the habitat. You have to build those kinds of contingencies into the system. The habitat, and the reason some are red and some are black, by the way, is the red ones are things I'm going to address in the environmental system, and the other things are things you need, but that are being addressed in the habitat or in other processes. So, for instance, you need visible and UV light available. You need mitigation of irradiation somehow. You need heat, managing the heat and pressure, and mitigating gas losses. You have to mitigate dealing with dust, and you have to have cleaning processes that can be, so when you use cleaning processes, like you think of like soap or industrial chemicals, those get back into the recycling process. So those things all have to be things that can be properly recycled and managed in your closed loop, but you still have significant cleaning because of funguses and bacteria and whatnot. So those processes have to be designed into this as well. You have to worry about healthcare, which I'm not going to talk about. You have to have a cycle for water and water purification and waste recycling. You have to have a method to produce proteins, fats, and carbs. You have to have a process for food processing and taking the things out of the system and making them into palatable foods and storing them for reserves. You have to have a process for, I call it import and export, but it could also be just stockpiles. But things like chips, repair parts, pharmaceuticals, food, spices, and flavorings, those kinds of things, you just aren't going to be in an early version of this kind of system. There's going to be exports also from, and the exports may be scientific samples, they may be Martian life, they may be, I have no idea, but there will be some kind of exports from this kind of a process. There's physiological and psychological support things you have to deal with, and I'm again not going to talk about those here, but there's issues with gravity. I'll not talk too much about that either. And then there's industrial things. There's a certain amount of machine parts that you need to be able to replace and not import. So you have to have the ability to 3D print parts. You have to have the ability to replace soft goods like clothing or bedding or rope or cabling. Things like that have to be able to be produced locally. And you have to have the ability to create organic polymers to use in these manufacturing processes. So you have feedstock for your 3D printing and whatnot. And this kind of gives you a real overview of what it would take to keep people going for a long period of time. I'm sure there's more smaller details, but this is a good top level overview. How close are we? Some of these things, like how to produce oxygen, we know how to do that. Carbon dioxide mitigation, we're even getting pretty good at that. Nitrogen, nobody's thought too much about that, but in a long-term habitat, to maintain a proper mix of air for people, we have to have a source of nitrogen, whether we take that out of minerals or on Mars, whether we take it out of the atmosphere, but it's not something people have worked too much. But in order to keep the balance of, you're going to have losses of atmosphere, and so you're going to have to restore the nitrogen balance, restore the nitrogen to keep that balance up. Purification of the air is also something that we haven't really dealt with as well as we should. They have filters and things like on the ISS, but most of the astronauts will tell you the smell and the condition of the atmosphere in the ISS is probably not something you want to live in for 15 years. So we need better molecular level filtration, and that's a process we have yet to develop. Electrical power, this kind of thing is going to consume significant power, and there's various ways to get that. I'm not going to include that in what I'm talking about, other than nuclear is probably the best choice. Wind and solar, geothermal is possible, but I also talk about backup fuels, hydrogen fuel cells. And the reason I included that is part of the fault tolerance or redundancy is what happens if electrical power source fails you. You still have to have your environmental systems run. Since your environmental systems are cracking water into oxygen and hydrogen anyway, saving that hydrogen and reusing it as a backup power source is probably a smart way to go, rather than waste the hydrogen. In habitat things, there's different things we have to deal with. Radiation mitigation is one that's not handled very well yet. We haven't got solved that, and I'm not going to solve that as part of an environmental system, but that's going to be more likely solved as where you put the habitat, how much dirt you put on you, and things like that. Biological cycle, creating protein, fats, and carbs. We've talked about that. People have built different things. I really think there's a couple of things about this I would like to talk about. One is you need a short cycle, which means you can't have a half a hectare greenhouse. You're going to, in a small habitat with 8 people, you're going to have processes that take waste, run them through a bioreactor, use the bioreactor to feed, to create feedstock for things like mealworms and duckweed and algae and bacterial cultures, things like that, where you get a very short cycle between the waste recovery and the producing proteins and fats and carbs. And then you're going to have to recreate those into food products that people actually want to eat using 3D printing and using flavorings and other things. That process is not developed, although people like that have developed, like Beyond Burger is a good example, are well into now developing how do you take plant proteins and make them into practical things. We need to take that farther and figure out how to use these kinds of shortly created products and turn them into palatable foods that people wouldn't mind living on for 15 years. Food storage, obviously you're going to have to keep a reserve of food, and you're going to have the ability to, you can't keep food for 15 years, so you're going to have to take it out of reserve and use it and recreate the reserve. So you have to have freezers and freeze drying and other capabilities to do that. Physical and psychological things I'm not going to talk about much. Freedom of movement is, I'm just mentioning that because the fact that you want to use spacesuits and go out of the habitat is one of the bigger losses of atmospheric gases. You know, every time you drive a rover out of a garage, or every time you go in a spacesuit and go through an airlock is an issue. So I left it on the chart. Industrial things. We have to talk about replacing hard goods and replacing soft goods, what kind of manufacturing tools we need to do that, and what are we going to use for feedstocks. Remanufacturing filters. Filters is going to be very important, both regular air filters and electrostatic filters and molecular filters. We're going to have to use all of those things to get a high quality atmosphere and maintain it for long periods of time. We're going to have a process to get water. Mining local ice is great, but what is that process for bringing the ice in, melting it, running it through purification, and making it usable in the cycle? Again, we're going to have a process for finding nitrogen. There is some nitrogen in the Martian atmosphere, and it may be possible to take it out of the atmosphere. I said taking it out of minerals here because that works on the moon as well, but we'll have to see what's the best choice. So that's part of the trade study thinking. It has to go into these kinds of things. Organic polymers, 3D printing is going to be very important because many of the things you're going to need in 15 years have to be either replaced or new things that have to be created, or you have to, you're going to want to build additional, who knows what, to keep going for that long. And so having a continual feedstock of polymers, and also you can use the polymers as binders to make cement-like materials, which you could use to expand things or build outdoor additional garages for, you won't even know what you'll need in 15 years in the future. So you have to have the ability for the people who are there locally to construct what they need. The gravity things, I'm not talking about too much, but you have to deal with bone density loss, muscle loss. The fact that a lot of the surgical techniques don't work under really low gravity, or may not work under really low gravity. You're probably going to need new drugs and some gene therapy things to deal. It's likely, in my view, and it's an opinion of mine that's unsubstantiated by any scientific data, that even though if you go from zero gravity, we know we have a problem with muscle loss and bone density loss. At Earth gravity, we don't have a problem. It seems likely somewhere in between we'll have less a problem than we have in zero gravity, but we'll still have a problem. That's my opinion. So we should start now looking at remediations for that. This gets into what I would call a reference model. And what it's trying to describe is what would all this look like put together into some kind of an actual technological solution. And you look at what does a person need? They need a sink, they need a toilet, they need a shower, they need food preparation. And to supply those things, they need an atmosphere that they can live in. They need heat, proper level of heat, temperature. So to supply those things, you're going to have a whole variety of things going on. You're going to have water being run through waste treatment, the waste treatment breaking down the material to feed back into the algae and the plants and the cultures that you need to create the food that you're going to then cycle back in and process and provide back to the people. You're going to need the ability to use those same feedstocks to create things like methane and biogas, and use those with CO2 and other things to create your polymer feedstocks. You're going to need electrolysis systems to create. And if you notice in here, there's two sources of, there's more than one source of everything. So for instance, you can get oxygen from the algae and the plants, but you also can get it from electrolysis of the water reserves. Likewise, you can get food stocks. You can break down the algae, if it's the right kind of algae anyway, into protein and carbs. You can have plants. You can also culture things much like yogurt. Yes. Question? 5 minutes. I'm reaching the end. I'm reaching the end of this too, so all good. So, so I'm going to skip this slide because of my 5 minutes. So anyway, to get into more details of this, I'm not going to get into all these details. I think if you want to study this all more, this will be all posted online, I'm sure. But the idea is there's a slide on atmospheric management, which says basically you have to have the air and processes and filtering, and you have to have reserves of different kinds of gases in order to do what you need to do. You're going to have reserves of oxygen, reserves of just plain compressed air for emergency purposes that's already a proper mix. You're going to have reserves of CO2, because CO2, even though for the most part CO2 is used up by the people, and there may be times when you actually produce more oxygen than you need, and need to have mix CO2 back into it to get the correct mix. And you also will use CO2 as a feedstock for making polymers and for accelerating the plant growth if you need the plant growth to be accelerated. So you have to have reserves of all those things. So you'll have to have pumps, you'll have to have all those different gases available. I also show a fuel cell for emergency power. You'll have to have all those things, and lakeways. This is the same kind of a picture for the waste management processes. So the waste management processes, you're taking in your various waste, not just from people, not just but also waste from food processing, waste from your industrial processes, waste from cleaning, all those things, and have to run those through bioreactors to basically kill all the viruses and bacteria, and then reprocess that into the feedstocks that you need for the plants and bacterial cultures and all those things. The amount of work that is not done on this is fairly large. All these things need to be thought through and studied and built into an actual working device. And that is something that I really am trying to inspire people to want to take on that task. Then there's another chart like this that talks about food and materials, where you take your food and process it, and that has to be made into palatable food, then put into storage. The food itself has to be produced. These are still yet simplified charts, and I can go farther with any of you if you'd like to talk to me about it further, but this is just a high level thing to present in the 30 minutes. So I think I'll skip this, but this talks about what processes yet need to be really developed and not just enhanced. It's where it's not just engineering, where actual science needs to be done. And last of all, assuming you have dirty ice and nitrogen bearing minerals and equipment and supplies from Earth and Martian air and dirty ice and all that, we have to do a trade study. We really need to put this all together. There are 20 different technologies for each of these. NASA's developed a lot of them. A lot of other companies and people have developed a lot. We got to look at all of these different choices for each of these elements and pick what is the optimum choice in an optimization. Then we have to build an Earth-based laboratory model of this that works. Then after that, the step is to go the Elon Musk thing and take that laboratory model and simplify it, reduce the number of pumps, reduce the number of pipes, and just simplify the living daylights out of it until it's an actual producible device. Then we have to build what I would call a initial production device that's suitable for testing on Earth. And if that all works and we get it debugged properly, we'll have something we can actually use. And we need to start the process to doing this because we're going to really need it. And that is pretty much my presentation. Questions? Yeah, all over. Yes. You very well could. I'm not talking about I didn't really talk about the habitat, but using water to protect, and actually many of these other gases in a liquefied form could also be radiation. So you could well build into the habitat the storage for all these things as part of the radiation shielding. Yes. Next.
2.1
Go for it.
and first, when do you get the training set for AI Because AI is only as good as its training set.
Yeah, it's exactly correct. And the answer to that is you have to build a laboratory model and then you have to. And then you have to stress it and push the envelope on all the different parameters and use all that data to drive back into your training model. It's a complicated process, but you need the system to be fairly self-optimizing, because you have to say, well, if the bacterial culture dies one day, what happens to the rest of the system to balance that up? Or another day, the oxygen pump fails, what happens? You know, you have to go through all those permutations of scenarios and feed those all into your AI model. So what's the other half of the question?
Payload for the big rocket that
Yes,
we all know that problems with not enough payload, seriously affected, all these, heavily vehicles we have before.
yes.
You know, knowing is interested in helping develop payloads for the geographic.
I would hope so, but I have no idea. Maybe I'll get a chance to talk to him about that at some point, but yes, I think he would be interested because he wants to go to Mars and stay there, and to do that, he'll need something like this. Yes,
Try to design out the system or see how much it would cost to build here.
I went farther than these pictures, but I won't even introduce that as a design. I do have an engineering degree, but I would say I've expanded the reference model from these slides, but it's not a design.
Do you have any guesses how much it'll cost to build your first prototype?
To build it or develop it. Developing it will cost a lot more than building it. I would say millions, probably realistically. It's going to take a team of some significantly smart people, probably at least a couple, probably several years realistically.
We're gonna take one last question.
Yes.
Without you stop the last.
Anybody else?
And use 3D printing with the brush.
Well, there's already a bunch of people who have done that. And my thought process is to keep the loop short, the closed cycle loop short. What you're going to end up with is basically protein powder, carbohydrates. You'll have some plants like tomatoes and things like that, but you aren't going to be able to build a giant greenhouse. So you've got to use these other processes. And so you will basically process those into materials that can be 3D printed, along with adding some flavorings and spices and things that are probably imported from Earth, and use those to 3D print facsimiles of food that are palatable enough that people can be happy to live on them. You know, and people have already done a lot of that work. There's already chocolate printers, there's printers that print pizzas. So it isn't something that's never been addressed. We just have to develop it farther to use the kinds of feedstocks you're going to get from this kind of a process.
Thank you, guys.
Yep. Thank you. Thank you all for coming this late in the day.